Hi, this is Benoit. Welcome to another episode of C++ for Arduino. You probably already heard me rant about the string class. Well, not in this video, because I will show you how we can write better programs with the string class. I usually recommend avoiding the string class because it produces inefficient programs. Unfortunately, it's not always possible to get rid of it. That's why this time I will show you 8 tips to improve your program while keeping the string class. What are we going to improve? We'll increase the speed, reduce the memory consumption, and avoid heap fragmentation. If you don't know what heap fragmentation is, please watch my other video on the topic. To benchmark the tips presented here, I modified the original string class to make it log each allocation and each duplication. To do that, I copied the original source code and moved it to a new namespace. So the name of the class is still string, but this one is in another namespace. In this namespace, I added new definition of the function that I wanted to monitor: malloc, free, strcpy, etc. Each of these delegates to the original function and then log the result. Because they are in the same namespace, my instrumented string class will use these functions instead of the originals. Here you can see the skeleton of the program that I will use for the rest of the video. Instead of putting the code in setup or loop, I defined a function in the new namespace to make sure that my instrumented string is used. Here is a simple function. All it does is creating a string. Well, there is a problem with this function. It doesn't put one string in RAM, but two. Indeed, the compiler already puts the string literal hello in the RAM. When this function runs, the constructor of string makes a copy of hello. We can avoid this copy by preventing the compiler from putting the literal in the RAM. We can do that with the f macro. Now, the constructor still makes a copy, but the original string is not in the RAM anymore, it's in the flash memory. Let's compare the two variants. The first variant calls strcpy, a function that copies from RAM to RAM, whereas the second calls strcpyp, a function that copies from flash to RAM. This proves that the original string isn't in the RAM anymore. As you can see, the addresses are quite different, because the two strings are in different address spaces. So that's tip number 1. Initialize your string objects from flash strings, because it avoids having the same string twice in the RAM. Suppose you have a string s, and you need to call a function, send, that takes an argument of type const**. There are two ways to convert a string to a char pointer. The first is to call toCharArray, which copies all the characters to an array. The second is to call cstr, which returns a pointer to the internal buffer of the string. Let's compare these two variants. As you can see, the first one makes an extra call to strncmp, a function that copies strings from RAM to RAM. By calling cstr, we avoid a costly duplication. but we must be careful of what we do with the return pointer, because it remains valid only if the string is unchanged. So that's tip number 2. Use CSTR instead of toCharArray because it avoids a useless copy. Compare these two functions. We can call both functions with a string instance, but the first one receives a copy, whereas the second receives a reference to the original. Let's run the program to see what happens. The first variant created a temporary string. You can see that because it calls malloc, strcpy, and free. So that's tip number 3. Pass objects by reference because it avoids a temporary copy. If you are stuck with a library that forces you to pass a string by value, you can avoid the duplication by using the move semantics of C++11. Suppose you constructed a string s. The normal way to pass s to a function is to write this. However, if you know that you will not use s after the call, you can move the object. Move converts s to an R-value reference, allowing to call the move constructor of string. This constructor rips off the content of s to create the argument for the function. So we cannot use s after that. Let's compare the two variants. As before, the first variant makes a temporary copy. The second doesn't make a copy, because it reuses the internal buffer from our original string. We can see an extra free 0 called from the destructor of s, but this call does nothing because the string was ripped of its buffer. So that's tip number 4. If you must pass by value, move the string. Suppose we have to compose a path for an HTTP request. We can use the plus operator because it has an intuitive syntax. Unfortunately, each call to this operator creates one or more temporary instances of string. To reduce the number of allocation, we need to avoid the plus operator. Instead, we can call the plus equal operator, which modifies the left side instead of creating a new string. Let's see how these two variants compare. As you can see, the first variant makes 1, 2, 3, 4, 5, 6 allocation and 1, 2, 3, 4, 5, 6 copies, whereas the second variant makes 1, 2, 3, 4 allocations and 1, 2, 3, 4 copies. So that's tip number 5. Mutate a string instead of creating temporaries. We can further reduce the number of allocation by calling reserve, which allocates a buffer of the specified size. If we reserve enough room, the string doesn't need to reallocate the buffer when we call plus equal. Let's run the program. As you can see, the second variant makes only 2 allocations. Reducing the number of allocations is not the only benefit of reserve. It also allocates blocks of constant size, 64 bytes in this example. Using blocks of constant size reduces the heap fragmentation as we saw in a previous video. So that's tip number 6. Call reserve, because it reduces the number of allocations and avoids heap fragmentation. In this example, we use the default constructor of string, which constructs the instance from an empty string. In other words, it's identical to this. Unfortunately, this default constructor allocates a block in the heap, even if we don't use that block at all. It allocates only 1 byte, so it's not a big deal, but we can avoid it by passing a null to the constructor. Let's see if this works. As you can see, we avoided the small allocation made by the default constructor. So that's tip number 7. Pass a null string to the constructor because it avoids a useless allocation. The C++ language allows concatenating string literals at compile time. They just need to be separated by spaces. For example, I can split this literal and the string will remain the same. To leverage this feature, we must substitute resource and API key with 2 string literals. The simplest way to do that is to replace the 2 variables with macros. The preprocessor will expand these macros before the compiler parses the code. Let's run the program to see the difference. As you can see, the second version makes only 1 allocation and 1 copy. So that's trick number 8. Compose strings at compile time because it reduces the work at runtime. More than ever, I invite you to check out the code samples on GitHub, so you can make your own experiments. I hope you enjoyed this video and see you soon with another one.